and their convergence test. First, I will explain what is a sequence and a series. After that, we'll say whether the sequence or series is convergence or not, or diverges. And we have a certain test. Uh, Based on the test, we can verify the series or sequence whether it's a converges or diverges. That is our objective today. That is our objective. Now, I will explain what is a sequence and a series. Then we can move to the convergence test and divergence test. Okay, we have certain tests. Okay, we can apply, and at the same time also we can see some of the problems. First, I will clearly explain the concept. Based on the concept, we can understand whether the sequence or series is converges or not. Okay, done. Okay, move to the session now. Okay, you can see my screen. Here, they clearly mentioned what is a sequence. It's a very simple one. You already know what is a function and all those things. Okay. Now, first you have to understand what is a sequence. Sequence is nothing but a function f. It's mapping from n to s, where n is a you know what capital N is a set of all natural numbers and s is it's a non-empty set. It's called a sequence. For example, here you can consider the n is a here you can consider the n is a domain. The domain is set of all natural numbers and it tends to certain numbers. For example, here the sequence is here n square because when you apply for the natural numbers for this sequence, it will get 1, 4, 9 up to it will goes on n square. Therefore, 1, 4, 9, up to it tends to n square. That is a sequence. More I will explain more clearly. Yeah, we can see the whiteboard. A sequence usually denoted by S. That means Sn or An. Okay, you can mention any one of the term. Here Sn tends to infinity. One Sn tends to n tends to infinity. That Sn is called as real numbers. At the same time, it is defined by certain domain and codomain. All those things. Okay. For example, here the function n is the function s is mapping from n to r. You may consider n to r. That means here the domain is n and the codomain is r. For example, here you can consider 1, 2, 3, 4 up to it will goes on. Okay, that is a domain. Our codomain is it's our sequence. That means that tends to r. That is a capital script r. That's me real number set of all real numbers. Okay, then 1 again you will get it. You will get it. That is a sequence 1. That is a partial sum. That's a partial sum of s1, s2, s3, s4 up to it will goes on. When you write this s1, s2, s3 up to s infinitive, then that is a sequence. For example, s1, s2, s3, s4. It is a sequence. Here sn is a function that's mapping from n to r. It may be any function. For example, here 1 by x power n. That means n is a, you know what to say n. N is a set of all natural numbers. If you apply here, you'll get it 1 by 1, 1 by here n square. You may consider n square 1 by 4 because when you substitute n equal to, you will get it 4. Then 1 by 9. Then 1 by, if you substitute n equal to 4 in this sense, you will get it 16. It will goes up to infinite. Okay, that is a sequence idea. Now, next we will see what is the series. I hope you can understand this diagram. For example, here the sequence is 1 by n cube. The next sequence is a constant sequence. Okay. For example, for any n, that value tends to 1. That is a constant sequence. And we have certain types of sequence. For example, finite sequence and infinite sequence. A sequence here they mentioned as a an. An is a sequence here. Suppose a sequence an which is tends to 0 for all n is greater than m, that belongs to capital N, said to be a finite sequence. So nothing but it's a finite sequence in the sense you may consider it's a, if you see the numbers in finite. So for example, S2 is equal to 1, 5, 6 up to 7 and 8. It's a finite sequence, okay, because it does not goes to infinity. Suppose if the sequence tends to infinity, in the sense that it's a infinite sequence. That's a simple one. Infinite sequence, nothing but which is not finite. Which is not finite in the sense it tends to infinity. That's a infinite sequence. First, what is the I clearly explain what is the sequence. Next one is we have two types of sequence. First one is finite sequence and infinite sequence. Now the next thing is we have the suppose the sequence is bounded below or bounded above. That's the thing. Okay. Now we can see that here we can consider. Here you can see the example 1 comma 1 by 2 comma 1 by 3 up to it will goes on. Here where n is a an is a sequence. The sequence is less than or equal to 1 because here the sequence is the maximum value of the sequence is 1. If you choose any number in between the sequence, definitely it should be less than. And then that sequence is called bounded above. For example, if you may consider in this previous problem, in the previous sequence, yeah, I will tell you the another example. 1 by n, you may consider that is a sequence. N, that is a sequence. It tends to n tends to 1 to infinity. You may consider an is a sequence. Then an tends to when an tends to 1 to infinity, then that means here an is equal to 1 by n. That means 1 by n tends to infinity. If you substitute any values here, we'll get 1 by 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, up to it will goes on 1 by it's certain number, okay, 1 by n and 1 by infinity will goes on, okay. For example, here 1 is the maximum value. Next that will reduce to 0.5. Definitely 1 by 3 is less than of 0.5. It may be a certain number 0.3. Then 0. It will goes on, okay. It tends to up to 0. Then the maximum value of the sequence is 1. That means an is greater than an is less than or equal to 1 because an is always less than or equal to 1. Then that if you satisfy this condition, that is a n is a bounded above of this sequence, okay. That is a bounded above definition. Next we see the bounded below definition. So bounded below definition is nothing but suppose you may consider the example, the same example when 1, 2, 3 up to it will goes on. Here the sequences you may consider n and an is a sequence where n tends to 1 to infinity. That means where here n is n, simply we consider n. Okay, when n tends to 1 to infinity, that means 1, 2, 3 up to it will goes on here infinity. Okay, it turns to up to infinity. Here you can see that here 1 is the small value. Okay, you may see that n is less than n is greater than or equal to an is greater than or equal to 1. Here always n is small value. That means that is a bounded below here. Then you can see the next example, third one. A sequence which is bounded above and bounded above and bounded below. It should be bounded. Okay, if you can see the table here. In this table, n tends to up to it goes on up to infinity, certain number 1, 2, 3, 4 up to infinity. Here an is a certain function. The given function is the given sequence is an equal to 1 power minus 1 power n 1 plus 1 by n. That is a sequence. If you apply n value in this sequence, you will get minus 2, 3 by 2, minus 4 by 3, 5 by 4, and it goes on up to infinity. If you plot the diagram, you will get a diagram like this. From the diagram, it's very clear that from the above diagram, you can see that small m is the bounded below and capital M is the bounded above. Here already they given the example here. Small m. Suppose an is less than or equal, greater than or equal to small m is that is bounded below, bounded on the left. Okay. Then suppose an is less than or equal to capital M, then that is a bounded above. Here after plotting this points, you can see that that is A1. The A1 in the sense that's the first point. A1, that is A2, A3, A4, up to it goes. Okay. Suppose the A1 point is -2, then A2 point is something 3 by 2. It will get, you will get it here. That is A by 2. Then A3, A4, A5. By saying all these values, here what is the very minimum value? That means small m. Small m in the sense bounded below. That is -2. Here you can see that m is equal to -2. That is a very small value. You can see that in this sequence, that is a very small value. Then when seeing all the numbers, capital M is the very maximum value. That is a bounded above. Therefore, definitely that sequence is bounded. Hence, we can say that sequence is bounded. Now, next we see the limits of the sequence. Limits of the sequence is nothing but, suppose when n tends to infinity. For example, you can see the example here. When you apply for the sequence, when you apply the sequence for limit, that means limit n tends to infinity, then an tends to certain L. Certain L is nothing but it's a some number, okay, is a finite number. Then that is a limit of this sequence. That is a limit of the sequence. Here the given example is an equal to n square plus 1 divided by 2n square plus 3. The sequence is tends to, if you apply the limit for that sequence, you will get it 1 by 2. That is a concept here. Now, convergent, divergent on the next, the convergent and divergent and oscillatory sequence. We can see that convergent sequence is nothing but if suppose the sequence is converges to certain finite number, that is convergent sequence. Divergence in the sense if you find the values plus infinity, if you otherwise minus infinity. If you say the sequence is the limit of the sequence is if you find the plus infinity or minus infinity, that is a divergent sequence. Then oscillatory sequence is sequence whether it's converges or diverges. We cannot be able to conclude that. You will get, sometimes you will get it both the values. It might be convergence. For example, the sequence is 2 comma 3 by 2, 4 comma by 4 by 3, 5 by 4. It tends up to infinity. Then here we may not conclude that it's a whether it's a convergence or divergence. Okay, that type of sequence is a oscillatory sequence. That's very important. Suppose a sequence is converges at a particular number, that is a convergent. If you apply for the limit, then divergence is if you when the sequence you apply for the limit, if tends to plus infinity or minus infinity, that is a divergent sequence. Then oscillatory sequence is whether the sequence is not converges, neither it may not be converges or neither. We cannot conclude that whether it's a convergence or divergence. That sequence is a oscillatory sequence. Now we can see one or two problems, then we can understand what is the limit of the sequence and all those things. For example, here we can mention an is a sequence. Here we can apply n tends to 1 tends to infinity. That is a sequence. Definitely we will get it. The sequence is 1 by n. Then when n tends to infinity, 1 tends to infinity. That means 1 comma 1 by 2 comma 1 by 3 up to it will goes on. That is an example of the sequence. Sometimes we may mention the an is equal to sn. We may mention different notation, an or sn or bn. It may be different notation. That is a sequence definition. The limit of the sequence is nothing but you can see the limit of the sequence. Suppose where n tends to infinity in the sense, then you may consider an minus, you may consider capital L if the modulus of an minus L less than epsilon. Here epsilon is a positive number. For all n is greater than or equal to capital N, that is a natural number. Okay. Suppose if the an approaches to L, capital L, that is a limit of that sequence. That's nothing but when limit n tends to infinity, an is equal to capital L. Okay, I will explain the problem very clearly. You may consider 1 by n when n tends to infinity in the sense when you apply the limit here, that means when limit n tends to infinity of an is equal to, definitely if you substitute the limit here, that means 1 by n equal to 0. Therefore, the limit of the value, the limit of the sequence is equal to 0. It's a finite number. Therefore, the sequence is, we can say that if you find the number sequence is finite number, that is a convergent. I already explained what is a convergent and what is a divergent. Now, that is a convergent sequence. At the same time, we can understand what is the limit of the sequence. We can see the another problem. We can see the another problem. The test of the convergent sequence. We may consider that is here one sequence. The sequence is here 2n square minus 1 by 3n square plus 1. Here you may consider that suppose the sequence is n tends to infinity, in the sense you can apply the limit here also. 2n square minus 1 by 3n square plus 1. Then n1 tends to infinity. Okay. Then if you substitute the limit, if you apply the limit in the sense that limit n tends to infinity, an is equal to limit n tends to infinity 2n square minus 1 divided by 3n square plus 1. Here, if you can apply the limit here. Here we can write limit n tends to infinity. For example, we can write the numerator as 2 minus 1 by n square divided by 3 plus 1 by n square. Now, if you apply the limit here, that 1 by infinity tends to infinity, therefore we will get it 1 by infinity tends to 0, okay, because it tends to 0. Therefore, 2 minus 0 by 3 plus 0 equal to 2 by 3. Therefore, the limit of the above sequence is, if the limit of the above sequence is equal to 2 by 3, then it's a finite number. Therefore, we can say that the sequence is convergence. Now we can understand what is a convergent. Suppose the sequence is infinite, in the sense that is a divergent sequence. Okay. Now we can see what is the series. I explained what is a sequence, then I explained what's a finite sequence and infinite sequence, and bounded above and bounded below, and oscillatory functions, oscillatory sequence, all those things. Also, I explained what is the limit of the sequence. Okay, then and you know what's a convergent and a divergent sequence. Suppose it is a convergent sequence. If you apply the limit, if the limit of the sequence is equal to finite, that means finite in the sense that is a convergent sequence. Then divergent in the sense, if you find here minus infinity or plus infinity, in the sense that is a divergent sequence. Then now we move to the next one, series. Now you can understand what is a sequence. Sequence is nothing but it is denoted by an, and n tends to 1 to infinity. It is usually denoted by any one of the function. 1 by 3n square you may consider. That is a sequence here. 1 tends to infinity. For all for all n belongs to capital N. That is a natural number, in the sense you will get it 1 by 3. Then 1 by 3. Next number, what's 1, 2, 3? It will go on. Okay. Next number 2 square. That means you will get the answer here. Then 1 by 3, 3 square. Then 1 by 3, 4 square. It will go on. Therefore 1 by 3, 1 by 3 into 4, you will get it 12. Then 9 into 3, I will get it answer 36. It will go on. Okay. That is a sequence here. Usually sequence is denoted by an. Then here 1 by 3, 1 by 12, 1 by 12, 1 by 36. It will go on. Okay. It will go on. That is a sequence. Okay. Now we see what is the series. The series is, you consider the sequence, then you can understand series. The expression of the following. For example, you may consider that an is equal to 1 by 3 plus 1 by 12 plus 1 by 36. It will go on up to infinity. Okay. If we add all those numbers, then that is a series of the functions. Series. That is a series. For example, series is usually denoted by summation 1 tends to infinity an. Then if you add all the numbers, then that is a series. Now, if you understand sequence, from that sequence you can understand the series. For example, here you may consider S1, S2, S3 because these are the numbers included in that sequence. S1, S2, S2, S1, S2, S3 is a, or we can say that it's a partial sum. Suppose S3 in the sense we have to add all the first three numbers. 1 by 3 plus 1 by 12 plus 1 by 36. That is a S3 value. Suppose S4 in the sense you have to add all the first four consecutive numbers. Okay, that is a partial sum. We can usually say that that is a partial sum of that series. Okay. Sequence and series series is nothing but usually Sn equal to you may consider S1, S2, S3, S4 up to it will goes on. Okay, up to it will goes on Sn. If you add all those values, that is a series. Usually it's denoted by summation Sn. That means n tends to 1 to infinity. That is a series. Sequence in the sense you can mention that Sn and n tends to infinity. That is a sequence. That is a small difference between series and sequence. If you understand sequence, then you can easily know what is a series. Here also the same thing. When the series is convergent or divergent or oscillatory, we can easily able to find. Suppose the summation n tends to 1 to infinity Sn is equal to, if you find it's a finite number, then that is a convergent series. Suppose if the series is divergent in sense, if it tends to minus infinity, suppose summation I1 tends to infinity equal to Sn equal to 5 or 6, it may be any finite number. Okay, it may be, it depends on the function Sn, depends on the Sn, it may be. Okay, it tends to a finite number and sense it's a convergent. If suppose it tends to minus infinity or past infinity in the sense, then that is a divergent. Oscillatory sense, you may not be able to get, if it does not tends to a unique limit, okay, for either finite or infinite, then that is a, you may not be able to get, it may not be a exact number, you may not get a unit limit. Okay, that is a oscillatory series. Now similarly you clearly understand sequence and the series. Now we are going to see the whether the sequence or series is converges or divergent. Okay, by using certain tests. Here we have many tests. For example, convergence or divergence test. Okay, and the next one is comparison test. I will explain what is a comparison test. Next we will see the comparison test. Suppose if we consider, suppose 0 less than or equal to an less than or equal to bn. Here an and bn is a sequence. For all n, small n, capital less than or equal to capital K. Capital K is a number or limit, okay, for some k. Then the sequence in the sense an and bn is a, you may consider that is a sequence or series. Okay, it's no problem. Series in the sense you should be summation n n tends to infinity. That's a sequence. Sorry, that is series. Sequence in the sense when n tends to infinity. Here divergence in the sense, once again, so divergence, I will see the example, you can understand what is a comparison test. You may consider summation n tends to 1 to infinity, then 1 divided by 1 plus n plus 1 the whole square, it's a converges. You may consider it's a converges. Then similarly we can write this one as a 1 divided by n plus 1 into n plus 1. Definitely it is less than or equal to 1 divided by n into n plus 1. Okay, suppose it is convergence in the sense which implies that summation n is equal to 1 to infinity 1 by n is converges. Because here 1 by n plus 1 is converges. N plus 1 the whole square is convergence. Then which implies that summation n tends to infinity 1 by n square it's a converges. Because here we can consider n plus 1, here we directly consider n square. That is a small difference, small example here. The next example, summation n tends to 1 to infinity. The second example, n tends to 1 to infinity 1 divided by square root of n diverges. Okay, here we can consider diverges. So diverges because 1 by n is less than or equal to 1 by square root of n. Because it's a definitely it's a divergence. Then the third example is 1 by n factorial. Summation n is equal to 1 to infinity 1 by n factorial converges because n square less than n factorial. Because whatever you choose the number here, n square in the sense you may substitute any real number here, you will get it. Definitely that value is less than or equal to n factorial. If you choose n equal to 2 in the sense 2 power square less than 2 factorial. Suppose for all, here for all n is greater than or equal to 4. If you satisfy this case in the sense it will true. N square, okay. For all n greater than, if you choose n equal to 5 in the sense, you can write 25 is less than 25 is less than 5 factorial. You know, it's a 5 factorial bigger value than 25. Therefore, it's a convergence. That is a small difference between comparison test. Now, limit comparison test. We have another test, the limit comparison test. And we will see the ratio test. We will see the ratio test. Then so ratio test. First consider one series. N summation n tends to infinity an. Here an is not equal to 0. It should not be 0 because the series should not equal to 0 for all n. Then if satisfies this condition, if the modulus of an plus 1 divided by an is less than or equal to q, then for all for 0 less than q less than 1, then the summation of summation n tends to infinity a modulus of an is converges. That is a ratio test. It's a one condition. That is the first condition. The second condition is if modulus of an plus 1 divided by an is greater than or equal to 1, then summation n tends to 1 to infinity an diverges. These are the two conditions in ratio test. It's very simple. First, you have to consider one sequence. If the sequence, the addition of that means modulus of an plus 1 divided by an is less than or equal to a certain number q. That certain number is 0 less than q less than 1 in the sense. Then we can say that the given sequence is converges. The second condition is suppose the value is greater than the modulus of an plus 1 by n is greater than or equal to 1 in the sense, then the sequence is divergence. These are the small concept. If you know this concept, we can easily apply the ratio test. We can substitute. We can see one problem here. You may consider the sequence n tends to 1 to infinity 1 by 1 factorial. You consider here that is a sequence here. In the sequence, an is equal to 1 by n factorial. That is a series. In this series, the an will equal to 1 by n factorial. That means 1 by 1 factorial, 1 by 2 factorial, 1 by 3 factorial. It will goes on up to 1 by n factorial. Okay. 1 by n factorial. Here, you can see the first condition. If the modulus of an plus 1 divided by an is less than or equal to q, it's a certain number. That means if you find the value is 0, 0 to 0 less than q less than 1, then it's a convergence. Therefore, here that value equal to an plus 1 by an is tends to 0, because you know that is n plus 1 factorial divided by n factorial is tends to 0, because that is a value here. An, you know what is that is 1 by n factorial. That means an plus 1 in the sense 1 by 1 n plus 1 factorial, n 1 plus 1 factorial divided by 1 by n factorial. Therefore, that value tends to 0. Definitely, the sequence of the series is convergence. Okay, that is one of the example here. We'll see the another example also. Summation n tends to 1 to infinity, n power n divided by n factorial diverges. When we can say that diverges, when we can say that that series diverges in the sense the modulus of an plus 1 divided by an is greater than or equal to 1, then series is diverges. Suppose the sequence is more than 1 in the sense the modulus of an plus 1 divided by an is more than 1 in the sense that is a divergent sequence. For example, here the value of this sequence is more than n. We can consider an plus 1 divided by an value is equal to 1 by 1 plus 1 by n the whole power n is tends to infinity. Sorry, it tends to e. Okay, if you apply the value, definitely it tends to e. Definitely e value is greater than 1. Therefore, if the value of the sequence is greater than 1 in the sense, therefore it's a divergence. That is another example for the divergence. First I explained what is a sequence and series, then convergence test. Next we are going to see root test. I explained what's a ratio test. Next we will see the root test. It's a very simple one. Root test also it's a very simple one. The condition is for the root test, the condition is if 0 less than or equal to an less than or equal to x power n. You may consider if the condition, that's a necessary condition, then or otherwise we can consider the another condition, 0 less than or equal to an power 1 by n less than or equal to x. Then for all x should be 0 less than x less than 1. Then we can say that then the series is converges. N summation n based on the condition we can verify based on the condition we can verify the root test. Now we can see the directly we can see the example here. First example, summation n is equal to 2 to infinity 1 by log n power n. So converges. We can say that the sequence is converges. The reason is, I will explain the reason here. Converges because you know the sequence here, because an power 1 by n is equal to, you know the root test sequence, because that value should be less than or equal to x. That value is equal to 1 by log n. Therefore, that tends to 0. If you have whatever value you substitute for n, that tends to 0. Therefore, it's a converges. The second example, we can see the second example. Summation n tends to 1 to infinity, n divided by n plus 1, the power n square. You may consider the second example because it is also converges. It's also converges. For example, here the condition here for the root test condition is 0 less than or equal to an power 1 by n is less than or equal to x. Then based on the condition, we can verify that the value of this one is an power 1 by n is equal to, we can consider here 1 divided by 1 plus 1 by n power n. Definitely this value is equal to 1 by e. This value is less than 1. Less than 1 in the sense we can say that that sequence is converges. Sorry, that series is converges. Okay. Now you know what is the root test. I explained 1 or 2 problems. Next, we can see some of the examples problem you can understand. Okay, now we'll see another test. We have many tests to check the series whether it's a convergence or divergence. We will see the another test, the limit comparison test. It's a very important limit comparison test. So limit comparison test. Suppose an, that's a series, an and bn is a series is greater than or equal to 0. Suppose an by bn is tends to L. Tends to L in the sense it may be any number. Okay. Then if the first condition, if L is belongs to the script that means a real number, then L is greater than or equal to 0, and if satisfy this condition in the sense, then summation that sequence summation n tends to infinity bn and summation n tends to infinity an is converges. You can say that. That is the first condition. The second condition is if L is belongs to script that's my real number. Okay, because L is that sequence an is one series, bn is bn also another series. If you divide the series in the sense it tends to the some L. So L in the sense it's a number. It may be a number. That number that's why I write here L is belongs to R. Then if and L is equal to 0, and we can if the L is equal to 0 in the sense summation the sequence of the series of bn summation n tends to infinity bn is converges. Then we can say that summation n is equal to 1 to infinity an converges. Okay, that is the second condition, second note. Then third one is if L tends to infinity and summation n equal to 1 to infinity bn diverges, then summation n equal to 1 to infinity an is a diverges. That is a condition. These are the condition. Suppose you may consider an and bn is a series. You may consider series. Then suppose an divided by n tends to L, it may be any number. Then if the first condition is if the L is belongs to R and L is greater than 0, then we can say that summation n tends to that sequence both the series is converges. An and bn also converges. Suppose that L value equal to 0 in the sense L value equal to 0 and bn is converges in the sense, then we can say that the numerator that is a an, the an is the an also converges here. The fourth one is suppose n tends to infinity in the sense infinity and bn diverges in the sense, then an also diverges. In more clearly, Here more clearly I will explain. Suppose A and you may consider one sequence, sorry, one series, then B and also another series. Here we can consider one series here. You may consider any series. It's a series, okay. Just consider as it's a series. It's also one series. So if you divide the series in the sense, definitely A and B n equal to a number. It may be any number, finite number. Suppose the first condition is when L tends to a greater than suppose the L value is, the first condition is L value is any number. It's a real number in the sense. Then at the same time Bn should be convergence. If sorry Bn also converges, then we can say the numerator is convergence as well as the when you divide the A and B and tends to L in the sense, then we can say that Bn also converges. Then series of Bn is also converges. The second condition is the same thing. Suppose L is a script any real number. Suppose L is real number in the sense. Suppose if you get the L value equal to 0 in the sense, then L value is 0 and the denominator value, that means the denominator series summation n is equal to 1 to infinity Bn is diverges. Bn diverges, then we can say that summation n equal to 1 to infinity n is diverges. Okay, that is a condition. Okay, these are the limit, that is a limit comparison test. Okay, I explained more than three tests: limit test, root test, and the convergence test or divergence test, and all those things. We'll see one or two exercise problems. Now we can understand. First, I will select the problem now. Okay. The question is, you may consider that is a series. We may 3 by 1 plus 4 by 8 plus 5 by 27 plus 6 by 64 plus up to it goes on. Okay, we may consider that is a one series. We are going to test whether it's a test the convergence, whether it's a convergence or divergence. So we are going to test now. First we have to consider un of the nth term. We can consider this term as the nth term of this series. We can consider that first term is equal to 3. The numerator, you may consider the numerator alone. If you consider 3, 4, 5, 6 up to it will goes on. It definitely is in the arithmetic progression. Therefore, we can write by using the arithmetic progression. We can find the nth term. That means Tn is equal to 3 plus n minus 1. Okay, n minus 1 into 1, that is equal to n plus 2. Okay, therefore the sequence that is a Tnth term. Similarly, in denominator we can consider 1, 8, 27, 64. It will goes on. That we may consider 1 cube, 2 cube, 3 cube up to 4 cube. It will goes on. That means 1, 8, 27, 64. In denominator you can see that is a denominator value. Denominator value, that is a numerator value. Numerator value we can consider in arithmetic progression, that is first term is a, then if the common difference in you know what is Tn value. If you apply by using the Tn formula, we can find the numerator, that is n plus 2. In denominator we can consider 1, 8, 27, 64. That means 1 cube, 2 cube, 3 cube up to it will goes on. Therefore we can conclude that is n cube. Therefore we can find the series now. Series is the an is equal to the numerator is n plus 2 divided by the denominator is n cube. that is a series here. When n tends to summation an, summation n tends to 1 to infinity, in the sense here also you can consider n tends to infinity. If you apply for n value, you will get the question. Okay, that means 3 by 1 plus 4 by 8, it will goes on. That is the answer. Okay, now next we have to verify the convergence stage. That is, suppose the highest degree of the nth numerator is 1 and the denominator is 3. You can see that you may consider for the n, the numerator is 1, the highest degree is 1 numerator, denominator is the highest degree is 3. Then we can see that we can consider Vn is equal to 1 by n minus 3 minus 1 equal to 1 by n square. Definitely it is a non-zero, it's a finite. If you see that, if you apply the limit, you will get, you can get that the limit of this one, the limit of the limit, if you apply the limit n tends to infinity for that an, definitely it should be a 1, exactly 1. Therefore it's a convergent sequence. The series is convergent. These are the one of the example for the convergence test. Similarly, we have many other problems. We can, the upcoming problems, we can see how to solve the another test. That means square test, root test, and limit comparison test and comparison test, all those tests. I hope you can understand what is the, how to check whether the series is convergence or divergence. In this class, I clearly I focused on the concept. Okay, based on the concept, you can apply the concept to the problem. You can get the answer whether it's a convergence or divergence. Okay, I hope you can understand this class.